Okay, good morning. So first of all, I would like to make a comment concerning something that I told you yesterday, and that was related to the definition of the crystal momentum. Yesterday, I wrote that K is equal to the crystal momentum, but that is not correct, since I had in mind the equivalence in the free electron picture between momentum and wave vector, since they are proportional. So sometimes you use momentum and wave vector to mean the same thing. So in this case, the correct statement is that h bar k is crystal momentum. So actually, h bar k is a momentum. In the free electron picture, we will see that also for block electrons that are not actually free electrons, h bar k will have the meaning of a momentum. But let's say for the moment, let's just add crystal in front of momentum to state that k in this case is the index, the quantum number that we obtain from Born-von-Kammann boundary conditions related to block electrons. And later we will see what is the actual meaning of this h bar k in the model of block electrons. Okay, so just to summarize what we saw yesterday. Yesterday we saw that the wave function that describes the electrons when the electrons are in presence of a periodic potential depends on two indexes. One is k and the other is n. K is the solution is a parameter that whose value is determined by the Born-von-Kammann boundary conditions. For the moment, I've not discussed the index n. I will discuss that shortly. Then we have the dependence on the position, and the dependence is such that we have a phase that is related to the value of k times a modulation, and the modulation has the same periodicity of the Bravais lattice where the electrons are moving. Due to this structure of the wave function of the block electrons, this function is not periodical in the real space because psi kn of r plus capital R is not equal to the same function, but is equal to psi of kn of r times a phase that is related to the vector of the translation. So actually, we have not the possibility to have an invariance under translations as is observed for the modulation. Differently, we have a periodicity. I just close the door. We have a periodicity in the reciprocal space, and the periodicity is the same periodicity of the reciprocal lattice. So G is a vector that belongs to the reciprocal lattice. Due to this periodicity, we have an equivalent periodicity of the energy, because if the wave function, once you make a translation of G, is equal to the wave function itself, this means that also the energy has to have the same property. So also the energy corresponding to K plus G has to be equal to the energy corresponding to K. Yesterday we saw that the K values that come from the Born-von-Kammann boundary conditions have a spacing that is a discrete spacing, but the size of the spacing is very small with respect to the size of the first Brillouin zone. Due to that, we may consider that the, let's say, K is a sort of continuous variable, as we did for the Sommerfeld picture. So the usual way to write down this equation and any other equation concerning energy is E of n. So n is again an index, a label, sorry, but K plus G becomes not is usually written not as a label or as an index, but as if you had a function, a continuous function that depends on something. So this is to stress the fact that the k variation is very, very fine in the reciprocal space. So we consider k also in this situation as a continuous variable. And this condition, as we will see shortly, has a strong effect on the structure of the electronic levels in the reciprocal space. One last comment before going on, two additional comments. One is concerning P. In the Sommerfeld picture, that means just for free electrons, we had that the Hamiltonian, so for free electrons, the Hamiltonian is invariant under translations, arbitrary translations. So this means that the electron momentum is a constant of motion. In the case of Bloch electrons, we have that H is invariant, but not under arbitrary translations. H is invariant only if you make a translation using a vector of the Bravais lattice. Otherwise, the potential is no more invariant. So we lose this feature. So this invariance is not observed also in the 4 Bloch electrons. So this has a consequence. So, oops, I just reconnect. Just a moment, I plug in the device because I think that the battery is not working. Yeah. So the last thing was that we had we have Bloch electrons, and in sorry for writing there. So let's say I use the same paper I had before. So in this case, h bar k is not a constant of motion. So as I told you yesterday, if you apply the momentum operator to a Bloch wave function, this is not a constant times the Bloch wave function. So the Bloch wave function is not an eigenstate of the momentum operator. But this doesn't mean that we are not able to evaluate the speed of the electron, because if we try to evaluate the expectation value of the momentum operator over the Bloch wave function, what we find is that this is equal to 1 divided by h bar gradient times the gradient of the energy evaluated with respect to the wave vector k. So it is still possible to estimate the speed of the electron during the motion of as the electron goes through the solid. That is and that is not proportional to k as it was for free electrons, but is proportional to the gradient of the energy. So this means that the direction of the speed of the electron depends on the gradient of the energy function evaluated at the value of k that corresponds to the electron we are investigating. So that in principle may be not the final result may not be proportional to k as it was for the free electron, but may have an arbitrary direction with respect to k that depends again on the gradient of the energy. So this is the first, another strong difference with respect to the free electron picture. And another comment was that I wanted to add before going on is related to the fact that since thanks to the block theorem, the Hamiltonian where H is an Hamiltonian that includes both the kinetic contribution and the potential contribution, due to the fact that it is possible to find a solution to that Hamiltonian. This means that on one side, that solution is stable. This means that if you have one electron that is described by that wave function is not expected to collapse or do something strange, but if then the electron is able to occupy that level forever if nothing interacts with the electron. For the Drude picture and from the Sommerfeld picture, the electron was not able to move freely within the solid, but in principle, one of the hypotheses of the models were that the electron and the ions are expected to collide during the motion of the electrons. So in principle, we should expect that if the electron moves according to those models within the lattice, then this fact may produce collisions on the electron. But the fact that here we are able to solve the Hamiltonian and find a wave function that satisfies that Hamiltonian, this means that that hypothesis is wrong, because in this Hamiltonian, we consider the presence of the lattice in a strict way, since we are including U of R, and U of R is an effect of the ions. So the fact that even if we consider the effect of the ions, we are able to find a wave function, this means that the physical motivation of the collisions is not due to the ions. So the fact that we have this solution means that the ions by themselves are not a source of collisions. So due to that, at this point, we have, let's say, no more references concerning possible physical mechanisms that may interact with the electron and produce what Drude and Sommerfeld called a collision. So an abrupt deviation of the speed, of the direction of the speed of the electron as the electron is moving within the solid. For the moment, so this means that if you pick up one electron at random in the system, and at some point the velocity of that electron is given by this expression, then that velocity stays there forever. So in principle, this system has a conductivity that is infinite at this point. As the real systems are not in this situation, so real systems have a conductivity that is not infinite, we have to assume that there is a mechanism that actually interferes with the electronic motion. But for the moment, again, this physical mechanism has no physical counterpart. So the physical motivation will be discussed in the second part of the lessons, but for the moment, we still keep this mechanism, and there is again a question mark concerning the physical motivation of the collisions. So again, for the moment, we do not know, again, what is the physical motivation of that. Now, what are the next steps? The next steps concern the different way we may use to evaluate this wave function and the corresponding and the corresponding energy values. So the steps of the discussion will be the following. First step, let's see what happens in the only case where we already know the solution. And the only case where we already know the solution is U of R equal to 0. Then we will switch on the potential. U of R will be different from 0, but not that strong. So again, different from 0, but small. So in this picture, you may consider U of R to be a perturbation of the free electron picture. As U of R equal to 0 and U of R small have been already discussed during the bachelor degree, I will just shortly review what happens there. Then, since the idea is to try to discuss the properties of all the electrons in the solid, not just the electrons that can be considered free or nearly free, there will be another part of the discussion when U of R is different from 0 and strong, so strong that the U of R resembles the atomic potential. So the atomic potential is the worst case for the point of view of the solid, because if the electron feels just the atomic potential, this means that the electron is bounded to the atom and is unable to move in the solid. So we will try to use a U of R that is close to the atomic one, but not exactly equal to that. So it will be possible to for the electron to move, to change position in the solid. Then we will try to summarize all the things, since maybe you have electrons that feel the atomic potential in some conditions, but in other conditions are also able to feel, let's say, a free electron situations. So there will be also another point where U of R is intermediate between the free electron picture and the atomic picture. So in this way, with this intermediate configuration, it will be possible to discuss electrons that fill all the possible configurations in the system. So both the free electron case, the atomic case, and something that is in between the two, these two configurations. So again, this and 1 and 2 will be just briefly reviewed to see what happens in those two configurations, while 3 and 4 will be discussed later in detail. Just to anticipate, point 3 will be what is called tight binding situation, where tight binding means strong binding between the atom and the electron. And in chemistry, the equivalent of that is LCAO, where LCAO is linear combination of atomic orbitals, to say that the electron feels the effect of the atomic potential, so the electronic configuration resembles the atomic configuration that you have for an isolated atom, so just atomic orbitals. U of R, the intermediate picture, will be handled using the pseudo potential method. And the pseudo potential method is a method that is based on the, let's say, on the integration within the potential, both of the contribution of the ions and also on the contribution of the core electrons. Because in general, let's say, we have that the ion is in principle a single positive charge, but we have that the nucleus, around the nucleus of the atom, we have electrons. Some of those are strictly connected to the nucleus. Some of those may move within the solid. The electrons that are strongly connected to the nucleus make a sort of contribution to the potential of the nucleus. So when the electron feels the nucleus, the electron does not feel just the positive charge of the nucleus, but feels also the negative contribution, the, let's say, positive potential due to the interaction with the electrons that are strongly bound to that nucleus. So this pseudo potential, we try to include in just one expression both the contribution to the potential coming from the ions and the contribution of the potential to the potential coming from the electrons that are strongly bound to the ion itself. So in this case, we will also consider core electrons, so electrons that are strongly bound to the ion. Okay, so I will now start with just a short review of these two pictures. So what happens if U of R is equal to 0? In this case, we already know the solution because the Schrödinger equation is just the Schrödinger equation that was found by Sommerfeld. So in this case, we know that the energy dependence as a function of the wave vector as a parabolic dependence. In this case, as we saw yesterday, now the wave vector can be described not in an arbitrary wave vector space, but is in the reciprocal space. In the reciprocal space, we have the division of the space that is made using primitive cells. We choose as a reference the primitive cell that is located centered at the origin, and that cell is called the first Brillouin zone. Now, just to make the diagram simple, I make the one-dimensional picture because I'm not able to make here a three-dimensional one. So this is just a one-dimensional picture. Later on, I will also try to describe the two-dimensional one. Just to make the calculation simple and the description simple, I will also assume that we are in a cubic lattice, so that also the reciprocal lattice is a cubic lattice. So I suppose to handle cubic lattices both in the direct space and in the reciprocal space. If this lattice spacing of the direct space, the cubic lattice spacing, is equal to A, the equivalent size in the reciprocal space is 2 pi divided by A. So let's say the size of the first Brillouin zone is 2 pi divided by A. If we choose as a reference the first Brillouin zone, that is the primitive cell centered at the origin, this means that we set the origin in the middle, so we have pi divided by A on one side and minus pi divided by A on the other side. So this is the, let's say, the size of this first Brillouin zone just in one dimension. At this point, the solution is the free electron solution, and the free electron solution is centered at the origin and has a parabolic dependence on the energy. But what we know from the fact that we are considering a block, so the block electrons, so the solution of the block theorem tells us that the energy has to be periodic. So in this case, in this diagram, what is the meaning of, let's make a translation using a vector of the reciprocal lattice. A vector of the reciprocal lattice is, for instance, a vector whose size is equal to the size of the zone. So if I make this translation, then this one translation using this vector, if I translate to the right, then if I make a translation, the final point is exactly in the middle of, let's say, the second Brillouin zone. So the zone that I find in this case on my right. Due to that, I have to find the same parabola also in this zone. So what I can do is to draw a parabola Yeah, that's not parabola, but looks like. And if I make this procedure using all the cells that I have in this space, this means that if I'm supposed to stay in the first Brillouin zone, what I find in that zone is this contribution coming from the, let's say, the initial parabola that was centered in that zone. Then I have these two branches that come from what happens in the second zone, one to the right and one to the left. Then I have additional branches up here that are related to what happens in a third zone, and so on. So if I make a representation just in the first zone, the final result is something like this. So I have many branches that intersect in the first zone the first Brillouin zone. And again, all those branches come from the parabola that is centered in all the other zones that are in the reciprocal space. And this way of representing the energy versus wave vector dependence just in one zone is called reduced is the so-called reduced representation, since you reduce all the energy dependence to be represented just in one zone. As what happens here has to be found in all the other zones, you may copy what happens here and replicate that in all the space. And in this case, you have a repeated representation. But for what we need, just one is fine. Just the reduced scheme is fine. And in this picture, we are also able to appreciate the effect of the second index of the electronic wave function, so index n, because if you pick up one value of k on the horizontal axis, on the wave vector axis, then what you find along the vertical direction with respect to k is that you have many different intersections between that vertical axis, let's say, and the branches that you have in the first zone. So you have one intersection here, one intersection here, another intersection here, and so on. So for each value of k, you have different values on the energy. These different values of the energy corresponding to just one value of k are indexed by the parameter n. So the n parameter is referred to the possible different energy values that you have when you fix the value of k. And so you have one, in this case, the first one, then you have the second, the third, the fourth, fifth, and so on. So in the index n represents all the different values. What is the meaning that is given? If you notice here, if you choose randomly one value of k along the horizontal axis, and then you evaluate, for instance, the first intersection is always part of this group of levels. So the first intersection will be always found there. That is a group of levels that in principle are discrete levels, but the space in between one level and the next is very, very small. So they form a sort of continuous group of levels. And the same happens if you consider the levels that correspond to n equal to 2, because for n equal to 2, you have for n equal to 2, you have always the levels that belong to these two parts of the branch. For n equal to 3, you have always levels in the other group, and so on for 4, 5, 6, and all the other possible n values. Due to that, the idea is to use the index n to group the levels in what is called a band. So for n equal to 1, when you say, I consider the levels corresponding to n equal to 1, you say, I consider the levels that belong to this part of the energy versus wave vector dependence, and all those levels are grouped into something that is called a band, and the band is a group of levels that are nearly continuously found one close to the other. So the index n is the index that refers to the band. So the index k refers to the wave vector, the index n refers to the band. Depending on the number of electrons that you have in the system, maybe you may host those electrons just in one band, or you may need 2 bands, 3 bands, depending again on the number of electrons that you have in the system. Yesterday we saw that one band, yesterday I told you that in the first Brillouin zone and in any other primitive cell of the reciprocal lattice, the number of electrons that can be hosted is equal to twice the number of ions, because the ratio between the volume of one primitive cell and the volume of one level is equal to n. So in one in one cell or in one zone, we may find n levels. N levels means 2n electrons. So this means that the first band is able to host 2n electrons. The second band, other 2n electrons. So in general, depending on if we make a reference to the Drude or the Sommerfeld model, depending on ZA, and ZA indicates how many electrons one atom is able to share with the solid. If ZA is equal to 1, this means 1 ion, 1 electron. So in total, you have n electrons, if n is the number of ions. So if you have just n electrons, this means that the first band is enough to host all those electrons. In this picture, if ZA is equal to 2, this means that you need to fill completely the first band to host 2n electrons. If ZA is equal to 3, then you completely fill the first band and you have half filled the second band, and so on, depending on the value of ZA. So the important thing here is that we have a strong deformation of the electronic band structure of within the system. Due to the periodicity, we have the appearance of different branches that are indexed by the n value. So here we have the appearance of different bands, while in the free electron picture, we may say that just one band. We had just the one parabola, so one band in this language. And yeah, so we have different energy levels now appearing in correspondence of just one value of k. Now, this means that this picture is true just if the electron is actually free. But in general, this is not the situation. So the second step is what happens when U of R is not zero, but U of R is slightly different from zero. So the next step is what happens when U of R can be considered to be different from zero, but small. If that is small, that is considered, the effect of that is considered through a perturbation to the U of R equal to zero situation. So at this point, one makes the assumption that the U of R, as stated here, is small, and tries to see what is the change induced in that diagram, Venn diagram structure, due to the fact that you switch on a perturbation that is considered to be negligible. The effect of that the fact that now U of R is different from zero as a main effect that is the removal of the degeneracy. In the previous diagram, we saw that if you pick up K here, then when this vertical line intersects any branch, then you have just one solution. So you have that at the intersection, the possible values, you have just one branch, so you have just one value of the energy corresponding to that K parameter. And in this picture, so if no degeneracy is observed, as in situation A, we have that E of n of that the energy that is obtained when U of R is different from zero but small can be considered to be equal to the energy when U of R is equal to zero. This equal means at the second order of approximation. So, sorry, first order of approximation. So if you make this, if you use the perturbation method to find the effect of this small U of R to the actual energy versus wave vector dependence, and you stop your evaluation at the first order in the perturbation, what you are able to detect is that at the first order in the perturbation, E of K in presence of the perturbation is equal to E of K when the perturbation is not there. So at the first order, of approximation, that is fine. You may also have a situation as you have here, if you consider the border of the zone or also the center of the zone. Here in the center of the zone, you have that in this intersection, you have two branches that are crossing, and the same situation is found here. So you may have configurations where for a fixed value of K, you have intersections, and when you have those intersections, you have two different branches crossing. So in principle, you have two different branches that are giving the same value of the energy. And in this picture that we may call B, so if degeneracy so if we are just like in B, then we have that E of n of k in presence of the potential is different from E of n of k in the free electron configuration. So the final point is that we may use as a first order of approximation the same energy band structure that we obtained in the free electron case everywhere, apart in the regions where we have that the band diagram in the free electron case displays a degeneracy. So in the case where we have crossing of branches, and what is found here, for instance, at the origin and at the border of the zones. So in those configurations, we have that the potential actually has an effect, and so produces what is generally called a gap. So if you remove the degeneracy, what is the consequence of that? The consequence is that instead of having two values of the energy that are equal with each other, you need to have two values of the energy that are different. So the fact that those are different means that there is a separation in between the two values, and this separation is called gap. So when you switch on the potential, what you obtain is a diagram that is very close to the free electron one, apart so here we have again the free electron picture where we have the degeneracy, we have a splitting of the energy values. So we have the appearance of this gap that now separates the bands. So while in the free electron configuration, as in the first picture here, up here, if you start from k equal to 0, energy equal to 0, then you may continuously reach any point of the band structure because all the possible branches are always interconnected with each other. So you may move from branch to branch without discontinuity. In the case a potential is switched on, then what you have is that this is no more possible. So if your electron is in one band, then if you change the energy of that electron in a continuous way, then it's not possible to move out of that band. To switch from one band to the next band, you need you have to give to the electron an additional amount of energy that is at least equal to the energy gap that separates the two bands. And the energy gap depends on the strength of the potential. So this gap is proportional to the, not to U, not directly to U, to the potential, but to the Fourier component of the potential that you evaluate at that value of the wave vector. So that depends on the Fourier component on the of the of the potential. And the physical motivation behind the fact that here you have nearly no deformation with respect to the free electron picture, but when you are here, you have a strong modification with the with respect to the free electron picture, is due to just to this point. If you, let's say, I make just a short comment on that. So just I have nearly 5 minutes more for the end of this first part. So I just make a very brief discussion about that. In general, we saw that when Bloch decided to solve, to demonstrate the problem, Bloch, so I just write explicitly the question. So why the gap when so why the appearance of the gap is observed only when the general C is found in the system and not when you have not the general C? Because again, when Bloch demonstrated the theorem, what happens if we suppose to try to demonstrate the theorem when U of R is equal to 0? If we demonstrate that when U of R is equal to 0, this means that I have to apply the Hamiltonian to the trial wave function that Bloch so Bloch used this trial wave function. If I apply that to the free electron case, then I have to do something like this. Now, if I apply this operator to the plane waves, then I have that k square comes down due to the second derivative. So I have the energy for the free electron. I may take the term that I have on the right side to the left side, and what I obtain is a sum over k of c k times so I have this equation. Due to the fact that the plane waves are a base for the wave function space, then if this summation is equal to 0, then all the coefficients of this summation has to be equal to 0. So this means that if I consider a specific value of the wave vector, so let's suppose that I decide to concentrate on wave vector that is equal to q. Then if q is here, so if q is in this position, what is the conclusion? That in this condition, only one value of the possible h bar squared k squared divided by 2m values will be exactly equal to the value of q. So if k is equal to q, then I have that in that case, the energy of the level will be exactly equal to that value. So the energy will be equal to h bar squared q squared divided by 2m. So what is found in this parenthesis is equal to 0. If what we find in the parenthesis is equal to 0 because the energy is equal to the free electron value, then the CQ coefficient can be different from 0. So CQ is different from 0. So what is the final point? The final point is if when I fix Q, just one value of the energy correspond to that Q, then for that specific value, the parenthesis is 0. If the parenthesis is 0, then the CQ coefficient can be different from 0. For any other value of the wave vector, the parenthesis is not 0 because the energy is different from the Q value. So the coefficient has to be 0. So the conclusion is, if you have no degeneracy, just one plane wave survives. So if you have no degeneracy, of all the combination that you put into the system, the Schrodinger equation to find a solution, just one term survives. Differently, if you have degeneracy, so if the condition corresponding to Q is a degenerate condition, then what you have is that when you consider the summation, there are at least two values of the of this summation that correspond to the energy you decided to choose. For instance, if you consider that point, you have that one value comes from the first branch, one value comes from the parabola that is centered in the first zone, the other value comes from the parabola, I'm sorry for this picture. The other value comes from the parabola that is centered in the second zone. So you have two energy values that correspond to you have two possible wave vectors that correspond to exactly the same value of the energy. So this means that for at least two values, of K, the parenthesis is 0 because that parenthesis is 0 for two different values of K. At this point, at least two coefficients are different from 0. So at least if two coefficients are different from 0, this means that when you apply the perturbation, in seeing the effect of the perturbation, you need to consider that the final solution can be a combination of all the possible wave functions that correspond to those coefficients. So So in this case, you need a combination of plane waves. what happens when you have a combination of plane waves? That you may find combinations using different coefficients. So one combination will give you one level, sorry, one combination will give you one value of the energy, the other combination will give you another value of the energy. And if you make the calculation, what you observe that if, for instance, if two plane waves contribute so if we consider a combination of different two plane waves, what you find is that in these two combinations, one of the two combinations has this so one combination corresponds to a solution, a combination of plane waves that is mainly located, that has a maximum amplitude, over the ions. So if one combination has the maximum amplitude over the ions, then this means that this combination is able to strongly feel the effect of the ion potential. Differently, what you find is that the second combination is a maximum amplitude has an amplitude that is maximum not over the ions, but in between two ions. So due to the fact that the amplitude of this combination is minimum over the ions, this means that this second combination doesn't feel the effect of the ionic potential in a strong way. So due to the fact that now the electrons are not in free space, but feel the effect of the ions that are located in the system, in the Bravais lattice, at this point, each combination has a value of the energy that depends on where the amplitude of that combination is maximum or minimum. So what is found is that the opening of the gap depends on the fact that, again, now if you change the wave function of the electron, the changing wave function may affect the capability of the electron to feel in a strong or less strong way the potential of the ions, and depending on the strength of the effect of the potential of the ions, then the energy of the wave function may be larger or smaller. So that is why you have this gap opening mainly when you have degeneracy. In other words, if you just work with one plane wave, then the effect of the potential is negligible. If you work with a combination of plane waves, then depending on the combination, the specific combination, you may have a different sensitivity to the effect of the potential, and so a different value for the energy of the corresponding level. So just briefly, this is why you have the opening of the gap only in presence of a degeneracy. Okay, maybe I talked too much. Now it's 10 past 10. So I stop here now. Do you have comments, or are there any comments or questions concerning this part, the initial part? Okay, so I stop now the registration. We make a short break and then we go on with the second part of the lesson.